since we have defined entropy for continuous random variable, we can talk about AEP, asymptotic equipartition property for random variables. So we talk about random variables x1, x2, xn. They are IID following the distribution fx. And we can talk about entropy rate, which is in this case is defined this way. So this entropy rate converges in probability to hx. Okay, so that's the AEP. Okay, and then from this definition of AEP, we can talk about the typical set. I have a shorthandedly notated A to be the typical set, but please be reminded that this set has two parameters. One is epsilon, the other one is n. Okay, so the probability of a typical set is close to 1. Okay, and then probability that x, a particular value of vector x, belongs to typical set is close to this number, 2 to the minus nh, as we have seen before, with the capital H x. So this probability was this one right here before, right? Or more detailed, this looks like that. So that is the place right here, right? For upper bound and lower bound, we have to take the plus sign inside the exponent, as I have done it right here. And the size of the typical set is going to be called volume of A, because this is non-discrete anymore. So this is continuous, so we have to have a different language to describe it. So for n-dimensional space, we can just say that it is going to be called volume of A. So volume of a typical set is upper bounded by 2 to the power of n hx plus epsilon. So that's the typical set part. And then we can talk about the volume of A more formally, just following the same approach that we have taken in the discrete case. Basically the integration of the probability density function is 1, and then only over the integration only over the set of a typical set A, then this is lower bounded by this one. This one is smaller than the whole integration. And using the bound that we had in previous page, then we can show that volume of typical set is upper bounded by this one. The same story that we have proved in the discrete random variable cases. And this is just the definition of Gaussian distribution function and entropy theorem that I have described, shown you a little earlier. So same result. Okay, and this one is relative entropy and mutual information. Basically, relative entropy is now integration, right, of f log or f over g. Okay, so relative entropy is the distance between two distributions, f and g, and it was defined with the summation. Now it is defined over, with the integration. So this is still the distance between two distribution F and G, but F and G are now continuous distribution. That's the only difference. And basically this one is still comes out to be non-negative. So using this one and the equality when F is equal to G, so this result we will still use. And if you have done that, basically the mutual information can be defined. So basically mutual information is, again, joint distribution versus product distribution. So that's the distance between joint distribution and product distribution. So most things stay the same as before, where we dealt with the discrete random variable cases, except just a few. So only those few items we need to be careful. One of the items was that we have discussed today is the entropy can be negative, but the volume, which is the size of the message set, is always non-negative. So here is the translation invariant property of differential entropy. So differential entropy x plus c, where c is a constant, is exactly equal to h of x. We can just use the uniform random variable or Gaussian random variable. So as you have noticed, Gaussian random variable has the entropy, which does not depend on its mean value. So x1 defined to be zero mean sigma square as variance, x2 same variance but different mean, which is 1. But when we talk about entropy of the two, they are the same. So translation invariance. So when we talk about translation, then the entropy doesn't change. But when we scale random variable with scaling constant a, then we have to be careful. Basically, we have adjustment term appears. So HAX is equal to HX plus log of absolute value of A. We have to be careful with that. So when we talk about multiplication by a constant, then the entropy changes. Okay, so we can take a look at that. And here is the most important part, which is to investigate what is the maximum entropy, of a random variable. What random variable? What distribution has the maximum differential entropy? But here we place on a power constraint. If we talk about just the maximum entropy, then probably we will again have a uniform distribution. But if we place power constraint, if we place constraint on covariance matrix, then Gaussian has the maximum entropy. So this statement is very important. So when we talk about noise or signal with a certain power constraint, then it is more useful in engineering sense. We can talk about a signal with a certain power. We can talk about noise with a certain power, right? In such a case, we can talk about signal to noise ratio based on the power, and then we can talk about we can describe the capacity of a search channel. Okay, so by placing power constraint, we can have a meaningful engineering problem. Okay, so what under power constraint, what is the signal that you have to use in order to have the maximum capacity? Okay, so in order to be able to investigate such problem, this is going to be a useful precursor. Okay, so let's define a random variable x. The random variable x has a zero mean and a covariance matrix K. So K is expectation of x and x transpose. So expectation of x and x transpose for 2x2 case is going to look something like this, and we are taking the expectation, then there is nothing but expectation of x1 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 x2 x2 x1 x2 x2. So this is going to be expectation of x1 x1 expectation of x1 x2 and so on, right? x2 expectation of x2 x1. So this we will call k11 k12 k21 k22 k22. Okay, so that's what the notation means for n-dimensional case. And in this case, the entropy is upper bounded by the entropy of the Gaussian. This is the Gaussian entropy. So the entropy of the Gaussian random vector. So that is the result. Okay, so for any random vector x whose mean and covariance defined this way has entropy upper bounded by the entropy of Gaussian random vector, okay, which has the same covariance matrix and mean, okay, but mean actually doesn't matter because it's it doesn't affect the entropy, okay, and the equality if and only if x itself is a Gaussian with a zero mean and covariance k. So we can prove this straightforward way. Basically, we can consider gx be any density with the same covariance matrix, and x has Gaussian distribution. Okay, so we can compare entropy of G and entropy of F. So we want to show that this is true. Okay, so this inequality holds. Okay, so that's the objective. So we want to show this, right, this objective, and then we can utilize the differential entropy is non-negative. So we can have differential entropy this way, and the first part is Hg minus Hg, and second part is expressed this way in detailed manner. So gx log fx dx. And then when we take log fx, fx is Gaussian, so it has this form. C1 is the constant term, and that's this part is the exponent of the exponential function. Okay, so that's the log fx. So when we substitute this into the integration, it comes out we have this term, gx times that term, and we note that this term, since gx has the same covariance matrix, this is exactly equal to the Gaussian, I mean, we can replace this with that one, okay? Because Gx also has the same covariance matrix, K. So we can replace this one is exactly equal to that one. And once we have done that, basically, we can have Gx replaced with the Fx, and there is nothing but the entropy of F. So once we have this, then we have proved what we need to prove. Okay, so that's the that is the end of the proof. Okay.